All right, so ethanolic / lactic acid fermentation, depending on the metabolic properties of whatever cell you're working with. So let's just keep in mind, if you've taken Gen Chem, great. If you haven't, you should have taken it by this point. But anyways, let's just keep in mind of Le Chatelier's principle about equilibrium, because that's going to really help understanding what's going on here. So we've already talked about glycolysis here. And in glycolysis, what are the two, I guess, big picture end products that we really need to get? Well, we get NADH, and we get, that's supposed to be P, pyruvate. Hopefully I'm spelling that right. But this is a 3-carbon molecule, and this is dense with a lot of electrons / hydrogen protons. And I say those two separately just because that's how it discerns them, but in reality it's just a hydrogen. But anyways, 3-carbon molecule pyruvate here. And we don't have oxygen available. There is no oxygen in our environment. So let's just say that we're the mitochondria in my muscle cells right now. I'm working out. I'm not getting enough oxygen delivered to me, and this is what's going to happen. So this is why I talked about Le Chatelier's principle. This NADH here is going to go through here to the pyruvate. And this is going to convert that pyruvate into lactic acid through a couple of other metabolic pathways. This is way more complicated than it actually looks. But if I have an acid, what does an acid mean? Well, it's something that has a very high number of hydrogen protons or hydronium in water. We're not really worried too much about that. But what does this give us as an end product, the lactic acid? Well, we're getting NAD+. Now, why would we do this? Lactic acid, yeah, I mean, my liver and kidneys and heart can break this down to some extent and use it. But if you've ever taken a CPR course and you know why you have to do chest compressions for the first 2 minutes before you shock them, it's because of this stuff. Because lactic acid gets in the heart and it actually messes with conduction. So yeah, a little bit of lactic acid, not that big of a deal. But in terms of if a bacteria or any cell really had to rely strictly on this unless it was accustomed to it, then you'd have really bad problems later on, because this is an acid, and acids aren't really good for keeping our proteins in their proper 3-dimensional form. But this gives us NAD+. So what is the benefit of this? So that this, I'll change colors here, so that this can keep on happening. Because what do we get out of this? We get ATP out of this. Okay? And this is where Le Chatelier's principle comes into play here. Because if I have, and I'll just draw it down here, let's just say hypothetical situation of A plus B reacts in equilibrium to give me C and D, okay? If I remove, I remove a product from something, then the reaction will go forward. And that's what this is, that's what's happening here. We are removing NADH, removing NADH. Giving it to pyruvate, converting it to lactic acid, we're getting NAD+ back, okay? This reaction can go forward, and as long as this reaction is going forward, we're getting some ATP out of it. We're not getting a lot of ATP out of it, but we are getting some ATP out of it. So that, if it's a last, life or death situation, some cells can do this, some cells can't. But too much lactic acid is going to kill you anyways. So that's the lactic acid fermentation. Keeping that in mind, let's talk about ethanolic fermentation. Again, we have glycolysis taking place. What does glycolysis give us? NADH. NADH. And pyruvate. I cannot spell like save my life. It's bad. 3-carbon molecule of pyruvate. We don't have oxygen available. No O2. And let's say that we're a plant and some brewers are trying to make us produce this stuff so that we can make beer. Well, what's going to happen? Well, this NADH is going to go to the pyruvate. It's going to donate a proton. This pyruvate is going to become lactic acid. I'm sorry, not lactic acid. Wow. ethanol. It's an alcohol. Alcohols have a lot of hydrogen in them. But if you know anything about, I guess, organic chemistry, you know that a 3-carbon molecule is an eth carbon. I'm sorry, a 2-carbon molecule is an eth molecule. Man, I don't know what's up with me today. So we're going from a 3-carbon to a 2-carbon. What have we given off in this process here? Well, we've given off CO2. So I guess if I were to highlight our products of this reaction, we get ethanol, CO2. Why do we have to do this though? These are just byproducts. What's really important is that we get NAD+, so that this reaction can keep going. So these are the products here. So these two, pretty much useless. CO2 isn't really that detrimental to the plant. In fact, it's quite beneficial. But ethanol is bad. Despite what, those of us that meet on Saturday nights may say, it is bad. It does pretty damaging to the cell, and there's not even, I can't think of any metabolic pathways that can use ethanol in plants. But what does this give us that's beneficial? Well, it gives us more NAD. It gives us more of our reactant, and it's removed some of our products so that glycolysis can keep happening, and so that we can keep making adenosine triphosphate. Cool.